stop the other screen sharing.
Yeah, it's fine. It's fine. It's
Yeah.
fine. Do that. Do that.
And then let's see, I'm going to do that one. We'll share that.
Yeah.
And okay, now you probably see my screen with the little thing down the side, all the little slides down the side. Let's see if we can fix that. And now you see either the presentation mode or the presentation.
Yeah, it's the presentation. It's fine. Yeah.
Oh, good. So you don't see two slides, you see one.
No.
Oh, wonderful. All right. So I've threaded that little needle. All right.
Okay, so the stage is yours. I'm disappearing. And,
thank you so much.
And just to energize you a bit, we have 360 people online at the moment.
Okay, wonderful. Well, hello, everybody. Here I am talking from the northern wilds of Illinois, where it is chilly outside. It's 34 degrees Fahrenheit, so pretty close to 0 Celsius, centigrade, however you say it. Today, what I'm going to be doing is talking about the Craftsman's Oath. This is a mixed talk. It starts out rather lightweight. We'll talk a little bit about the history of programming and where we all came from and why we're all here. And then towards the end, we're going to get into some ethical issues. So hold on to your hats because this one should be fun. So I'm going to go start back at like the 1940s when all of this software stuff really began. And you can make the argument that it actually began before that, but I'm going to draw the line at this guy here, Alan Turing. I'm going to say software really began here in 1936 when Alan Turing wrote his wonderful paper with an incomprehensible title, right? On computable numbers with the application to the Einscheidungsproblem. I'm not going to get into any depth here about what this paper was. However, I do encourage you to study this paper and read this paper. And one of the best ways to do that is to get Charles Petzold's wonderful book, The Annotated Turing. In this book, Charles reprints the entire paper, but then surrounds it with historical anecdotes and explanations and makes it comprehensible. Otherwise, the paper is very thick going. I've read Charles's book twice. I'm going to read it a third time. It's a masterwork in the explanation of what Alan Turing was up to. But Alan Turing, in that paper, more or less founded the idea of what software is. He did that inadvertently. His goal was really to solve some obscure mathematical problem, but in so doing, he pretty much invented what we would call software today. And that set him on the road to dealing with computing machines. So as we all know, he helped decode the Enigma codes during World War II and helped the Allies win World War II and so on. The kinds of devices he was using were these interesting little devices here called relays. A relay is just an electromagnetic coil. You can see the coil sitting there. And if you run current through the coil, you will get a magnetic field. And the magnetic field will attract that little lever that's over to the right there. And that little lever will move the switch contacts that you see at the bottom. And so it's an electrically activated switch. It's called a relay because telegraphers, the guys doing Morse code with the keys and the clackers, those guys used relays to relay the signal down the line because, the signal's not going to go very far, about 10 miles before it peters out. So they would use this to relay it down the line so that the signal could go hundreds or thousands of miles. These little devices can operate at a rate of about 10 cycles per second. So that was kind of the clock rate, 10 hertz. But that was faster than a human could think for these particular kinds of operations. The folks who built the bomb, the machine that decoded the Enigma, realized that they could go much faster if they used vacuum tubes. But vacuum tubes were not reliable in those days. They weren't being mass produced in any kind of quantity. And they used a lot of power and they burned out a lot. And it was very difficult to build any kind of a machine that used more than 3 or 4 vacuum tubes because there was always one that was burning out. So that problem wasn't really solved until about 1945. And even then it was iffy. But by 1945, they had managed to create an actual computer. Now, Alan Turing was deeply involved with this computer. This is the ACE, the automated computing engine. He helped to design the machine, and he wrote most of the software in the early days, if you can call it software, that ran on this machine. A brief sojourn into the memory. This machine was supposed to use mercury delay lines for the memory. Mercury delay lines are a tube full of mercury. You put a speaker at one end and a microphone at the other. You pump bits into the speaker and then you listen to them at the other end, and then you wrap them around electronically. So this was rotating memory. The memory itself was the sound waves through the mercury. And by the way, the speed of sound through mercury is pretty doggone fast. So this was really quick memory. The problem with it is that every time a truck drove by on the road, it shook the mercury and destroyed the contents of memory. So eventually they fell back on this approach, which was cathode ray tube memory. Some of you out there will remember what a cathode ray tube is. Those of us who've been programming for 20 or 30 years or more, we've used cathode ray tubes in our monitors. And some of you may remember television sets from the early days where, you would turn the television off and the picture would slowly recede until you had this little dot on the screen. Those were cathode ray tubes. And a cathode ray tube works by using an electron beam that it sweeps across the phosphors on the surface. And the thing about that electron beam is that it can deposit a charge on the screen. And if you sweep the beam past that charge, you will detect that the charge exists because the current in the beam reduces or increases slightly. So there was a way to read what was written on the screen, and that gave you a kind of memory. It also served as Alan Turing's output device because he could actually see the results of his programs by looking at memory, literally looking at memory. He would just look at the screen and see the bits that were there. Now, I want you to imagine what it was like for Alan Turing in 1945 to write software for this machine. There was no language other than the primitive binary code of the machine. So he had to write in binary. Now, if you have never written in binary, this is something you should try one day. Get some emulator of an old computer and see if you can write a very simple program in just raw binary. You can use octal or hexadecimal if you want. As a matter of fact, Alan Turing used base 32. So he spends a year doing this, and he's writing very interesting stuff. Like, he's got to use binary for everything. He doesn't have a subtract instruction, so he has to emulate subtraction by using the 2's complement. You understand that probably. And he had to invent the idea of a subroutine. When they built the machine, they hadn't even thought about subroutines. And so he had to figure out how to remember the return address on a stack. He actually invented the concept of a stack. And his push and pop methods were called bury and unbury. He actually had to write a floating point package. Try that one day. Just write a floating point package. Write it in C, write it in Java. It doesn't matter. Just try and do floating point arithmetic with raw integers, and you'll see what kind of a challenge that was. He did it in raw binary, and he did it because he needed to do some mathematical analysis, and for that you need floating point numbers. So for a year, this is what he was doing, and this had to be really, really nitty-gritty work. But then he gave a talk. And it was about a year later he gave this talk. And this talk was transcribed. Some people wrote it down. And in this talk, he said 2 very interesting things. First thing he said, we shall need a great number of mathematicians of ability. Is that what you are? Are you a mathematician of ability? Is that what a programmer is? A mathematician of ability? But look what he says after that. because there will probably be a good deal of work of this kind to be done. How did he know? How did he know, that there would be an awful lot of work of this kind to be done? I don't think he had a clue as to where we would all wind up with this. But it's an interesting statement nonetheless. He realized even then that the demand for programmers was going to be high. But then he went on to say something even more interesting. He said, one of our difficulties will be the maintenance of an appropriate discipline so that we do not lose track of what we are doing. Is there a better statement about what programming is like? Some kind of discipline so that we do not lose track of what we are doing. Anybody out there lost track of what they were doing? You're writing a bunch of codes. Where the hell am I? How did he know? Well, he experienced this just out of hand, right? He just knew. He had written all that binary code. So yeah, he understood that you need a kind of discipline, otherwise you're going to lose track of what you're doing. So now we begin a frantic run through the history of computers. Starting in 1945, the number of computers in the world is on the order of 1. I use big O notation, on the order of 1. Maybe there's 2, maybe there's 5. At some point, there was 1. And how many programmers were there in the world? Well, at some point, there was 1. Before that, there were 0. And then there was 1. That 1 I say is Alan Turing. There are other people who it could have been. But the point is that we're on the order of 1 programmer in the world. Things moved forward. By 1950, the memory problem had been improved. We weren't using cathode ray tubes anymore, or at least most people weren't. Now we were using core memory. And I'm not going to describe how core memory works, except to say that core memory is remembered. The memory is remembered on those little metal rings that you see there. They're about 1 millimeter in diameter, and they record bits using magnetic fields. And they can you can change the bits by running the right kind of current through those wires. These were really expensive. By the way, this was the most common form of memory from the 50s, 60s, 70s, and even into the 80s, right? There was core memory out there. Some of you have had a program crash in Unix, and the crash report goes into a little file named core. That's the reason it's called core. It actually was core memory. We called it core back in those days. We would say to each other, what's in core today? So this was core memory. The cost of core memory was on the order of $1 per bit. A megabyte would have cost around $8 million, or $9 million, because there was always a parity bit in those days. That's because core memory was not perfectly reliable. What was getting more reliable were the vacuum tubes. They were getting mass produced at a much greater rate. They were becoming more consistent, more reliable. Their power consumption had gone down, and it became feasible for businesses like IBM to conceive of building machines, building them, almost mass producing them, not quite mass producing, but building them in some quantity, a reasonable number of machines. This is the era of the language. John Bacchus submitted the Fortran spec in 1953. I was born in 1952. I am older than Fortran. I'm not sure I should claim that, but I am older than Fortran. The code you see on the screen here, that's a little bit of Fortran code. And just to give you an idea of what this language was like, look at line 703 down there. That's called an arithmetic if statement. And it's like an if statement that we would use today, except, well, let's just read it. If the quantity IA plus IB minus IC, if it's negative, go to line 777. If it's 0, go to line 777. If it's positive, go to line 704. The if statement was really just a go-to statement with a 3-way split. Notice the line numbers. The line numbers look like they are ordinal, but if you read carefully, you'll realize that they are not ordinal. For example, if you go down to the bottom, you'll see a line number 601 long after line 799. The line numbers were not ordinal at all. You could have them in any order you want. They were just labels. That's all they were. And you might wonder, well, why didn't they use alphanumeric labels? That would have been better. And the reason for that is that alphanumerics took more memory than numerics. So to save memory, they used numeric line numbers. It's just wonderful. By the way, we wrote this code on punch cards. Actually, we punched the code on punch cards. We wrote the code on paper using pencil. Programmers in those days did not know how to use a keyboard. Programmers could not type. We wrote with pencil and paper and used an eraser quite a bit. This is the era of Lisp. Lisp was invented at around this time, before 1960. Functional programming was there in 1958. It was there before object-oriented programming. It was there before structured programming. Functional programming was the first of the paradigms to be discovered, implemented, whatever word you want. But by 1954 through 1960, IBM had built and sold, not sold, rented. IBM didn't sell computers. They were far too expensive to buy. You rented machines from IBM, and they had built and rented 140 of these big vacuum tube computers. And they ran things like Fortran and Lisp. And in the end, they also ran COBOL, but in the early days, they didn't because there was no COBOL. And notice these machines, big, horky machines, very slow by today's standards, very little memory by today's standards. Maybe it would have 4K, maybe 8K if you were lucky. Notice who is sitting at the card reader. In those days, most programmers were women. Men built the hardware, women programmed the computer. That was the way the labor was divided in the 1950s. That seemed to fit the way they thought about things. And in fact, women dominated the field quite a bit. This is Grace Hopper. Grace Hopper got into this a long time ago. Back during World War II, she got into the whole digital electronics thing and got into information processing. And then eventually she became we'd call her the CTO of Sperry Univac, right? But they didn't call her a CTO back then. I don't know what they called her. She was also a high-ranking officer in the Navy and was deeply responsible for the evolution of languages. This is the person who invented the word compiler. The reason we talk about compilers today is because she coined the term. She actually wrote the very first compiler ever. It was a compiler called A0 that nobody knows much about anymore, but she was the one who got that ball rolling. In the end, she was also deeply instrumental in the creation of the COBOL language, which we're not going to blame her for because it was a good idea that had a bad implementation. Let me just say that about COBOL as being someone who survived working in COBOL. Here are all the programmers on the ENIAC computer at Princeton in the 1950s. This is one of the big computers of the day, and it was not programmed with a language. It was programmed with punch cords. You actually pushed cords into slots. And by the way, that's even harder than programming in binary. So give some kudos to the women who are programming this machine because that was not easy stuff. By the end of the 50s, the number of computers in the world was on the order of 100. Okay, there weren't a lot of machines yet. They were still very expensive. They were very difficult to build. They were unreliable. It took massive facilities to house them. So there weren't a lot of computers in the world. Maybe there were 200, maybe there were 500. It was on the order of 100. The number of programmers, however, was about 10 times that. And the reason for that was that there weren't any frameworks in those days. There wasn't any internet. You couldn't download anything. There was no code to reuse. If the code executed on the computer, it was because you wrote the code. So she had to write everything. And by the way, there weren't a lot of operating systems. And what operating systems they were pretty small. Most computers had no operating system at all. So you had to write everything, right? And these machines were terribly expensive. And so to justify them, they had to be kept operating 24/7. And therefore, you needed a very large number of programmers just to keep the machine going. Now, who were these programmers? Well, there were no courses to take. You couldn't go to school to become a programmer, right? So they drew the programmers from engineers and scientists and mathematicians who were already working. These were old people, right? These were people in their 30s, late 30s, their 40s, their 50s, their 60s, people who had been around a long time, who had a nice mathematical bent, Alan Turing, mathematicians of ability. These are the kinds of people that were the original programmers. And those people wrote the code that ran in those machines in those early days. But the technology was changing, and it was changing really fast. The transistor had been invented several decades before, and it very quickly found its way into these machines. The benefit of a transistor is that it's much smaller. It consumes almost no power. It's as fast as a vacuum tube, and it's much more reliable. It doesn't burn out, or doesn't usually burn out. And so building computers out of transistors became the obvious solution. By 1965, IBM had produced over 10,000 of these 1401 machines. These machines were lovely little machines. They worked in base 10. IBM, being a business machine company, decided that business is done in base 10, therefore this computer will operate in base 10. So all of the electronics inside was wired up for decimal mathematics. The numbers were actually stored in binary, but it was 4 bits per decimal digit, binary coded decimal. This extended all the way into the address arithmetic. So this machine was shipped with 4,000 words of core, 4,000 bytes of core, 4000, not 4096. Powers of 2 were not a thing in this machine. You could rent one of these things for $2,500 a month in 1965, which is a lot of money. And in 1965, it was a lot more money back then. But still, that was in reach of mid-range companies. Mid-range companies could rent one of these things and then get a staff of programmers and do all of their information work, payroll and accounts payable and inventory and general ledger and all this stuff that they could get done on a computer like this. So they sold or rented like hotcakes. So by 1965, the number of computers in the world is on the order of 10,000. The number of programmers in the world, still 10 times larger, had to be on the order of 100,000. Now, who were those guys? Who were those programmers? This 100,000 computers. Well, I was one of them. I was actually not one of them. I was 13 at the time. Not quite a programmer, although I had written some code by this time. Not code that you would recognize. It was on a little computer that had 3 bits. It was plastic. You cycled it manually. You programmed it by putting little tubes on pegs, but it was a digital computer, a 3-bit finite state machine that convinced me that I wanted to be a programmer for the rest of my life. So who were all these programmers? Well, there were not enough engineers and scientists and mathematicians to draw from. There weren't any CS grads yet. Nobody was graduating college with knowing how to write code. So these programmers were drawn from the best and the brightest of the other people in the company, people like accountants and planners and marketing people, anybody who had a kind of technical aptitude. And in fact, this was the era of the aptitude test. People would take tests to see if they had the aptitude for programming. Companies would deliver that test to all of their people and go, do you have the aptitude for programming? We need programmers. And that's who these people ended up being. By 1966, IBM was producing thousands of 360s, beautiful machines, wonderful machines. I worked on IBM 360s in my first year as programmer. Lovely machines. Look at the lights. Look at the lights on the front panel. You could tell a lot of what was going on by looking at those lights. Look at the pattern of the lights blinking back and forth. You could debug your code just by staring at the lights. This is the era in which object-oriented programming was invented. Ole Johan Dahl, Christian Nygaard invent that in Oslo in 1965. They put it in a language called Simula 67. This is also the era of functional programming. Edsger Dijkstra comes out with this idea that maybe GoTo might not be such a good idea. This is also the era where Ken Thompson and Dennis Ritchie, borrowing time on a PDP-7 up on a floor above them, invented two things. Between projects, you know, they weren't doing anything important. They invented C and Unix and changed the world. But the world was changing faster than even they thought, because by 1970, integrated circuits were being put into these computers. Digital Equipment Corporation had been founded. They had produced 50,000 PDP-8s already by that time. The number of computers in the world was now on the order of hundreds of thousands. The number of programmers in the world by 1970 was already on the order of millions. We are only 25 years after Alan Turing. 25 years, and we've already got on the order of millions of programmers. Look at that timeline. That's not a long time, and that's a crazy rate of speed. Hundreds of thousands of computers, millions of programmers. Who were these programmers? Well, I was one of them. That's me at 18, 1970. Yep, I was already a programmer at that time. I got hired by a company to write code on an IBM 360 and on some mini computers. I didn't go to college to do that. I had already kind of taught myself COBOL and Fortran and PL1 and assembly language and a bunch of other languages. So I got hired right out of high school and into a programming job. And I was not alone, although most programmers now were graduating from university degrees. There were tens of thousands of CS and EE grads pouring out of the universities, ready to write code. Programming had become a career. And all these graduates coming out had something in common. They were all young and they were almost all male for some reason. Don't know why, don't understand why, but they were almost all male. In 1970, the first job I got, there were 24 programmers at this company. Most were in their 30s and 40s. There were some in their 50s. They were mostly older people coming from that previous cohort. And at least half of them were women. There were a lot of women programmers where I worked during my first job. But 10 years later, I was working at a different company entirely. They had about 50 programmers. We were all in our 20s or early 30s, and maybe 3 of them were women. The shift had occurred. The shift gets recorded in this graph. In this graph here, this is STEM fields, women in STEM fields entering university to study STEM. And you can see the green lines are the non-computer science ones, and the red line is computer science. And they show the peak at roughly around 1985. I think they missed that. I think the peak was actually around 1975 or 74, something like that. At least my experience was that the demographic shift occurred in the 70s, not the 80s. But the graph is still very interesting. It shows an obvious change in the demographics of computer science, a change that I cannot explain, and I'm not going to try to explain. Businesses at this time had to have programmers. And what very young men lack in discipline, you know, Alan Turing, appropriate discipline, they make up for with energy. Talk to a 22-year-old programmer, ask him to work 80 hours a week. We did in those days. We were stupid, but we would put in really dumb hours, crazy hours, and we would do it for almost no money. My salary as a young programmer was $6,800 a year. And for me, that was infinite. You know, I could make my car payment, I could give my parents a little rent, and life was good. And my salary went up very rapidly over the next 10 years. Now, remember, up to this point, programmers were disciplined professionals right? They had been taken from the working community, right? They hadn't graduated school. They had been older people. They didn't need a lot of management or process. They knew how to manage their time and communicate and work together. These were the original programmers, the older programmers. They understood deadlines and commitments and what to leave in and what to leave out, you know, the old Bob Seger song. And they had worked miracles. These are the people who wrote the IBM 360 virtual memory operating system. My God, virtual memory, what a concept. Holy cow. These are the people who put us on the moon, put us into space. These programmers worked at NASA. They wrote the code for the Apollo. They wrote it for Mercury and Gemini and all the fighter jets and submarines. These were the people who invented structured programming, functional programming, object-oriented programming. These were the programmers who created Fortran and COBOL and ALGOL and Lisp and C and Unix. Those original programmers knew how to get big things done with very limited resources. And what process did they use to achieve those big things? Well, if we could have observed it, we would say today that it was agile, because they worked in small cycles and they did lots of testing. The Mercury space capsule programmers, for example, wrote their unit tests in the morning and made them pass in the afternoon. They did a kind of, test-driven development. And most of them used a weekly or bi-weekly cycle. So they were using something that we would have thought was agile. But here we are in the beginning of the 1970s, and hordes of young testosterone-driven men are pouring into the industry, and they need management. They don't know what the hell they're doing. They've never worked anywhere in their past. They don't know what schedules are. They don't have the discipline for that. They need management. They need a fixed process. And it just so happened that a fixed process was there waiting for them. Nowadays, we might call that waterfall. I'm not going to go into the history of waterfall or tell you what it was. I'm just going to say that from 1945 to 1970, we were using an ad hoc process that we would probably today look at and think was kind of agile. From 1970 to the year 2000, we were in the waterfall era. But things were still moving like crazy. By the 1980s, the personal computer era had begun, and the number of computers in the world, well, it's on the order of something really scary. The number of computers just goes through the roof. What's happening to the number of programmers? Well, that's going up too. It's going up really fast, probably on the order of tens of millions by this time, by the 1980s. And we're into the 80s and we're into the 90s and we're into the waterfall era. And these early programmers that got hired in the 70s are now getting older and older, like me. And we reach a point and say, wait a minute, something's going wrong. We can't keep doing this waterfall nonsense. And so 30 years into the waterfall era, we have the Snowbird meeting and we have the Agile Manifesto. And we thought we were changing the world. Yeah, and we did. I mean, there was a heck of a lot of change that occurred, but the change around us was even increasing, because look at what's happened since 2000. We've got the web. Do you remember a time when there was not a web? We've got frameworks coming out of every orifice of every programmer's body. We've got languages coming out the wazoo. We've got Swift and Dart and who knows? There's just a zillion languages. There are more languages now than there were. There are processes coming out. Everybody tried different processes. We've got practices. We've got platforms. There's just so much stuff. And the number of computers in the world, well, it's on the order of infinite now. There's no way I could even begin to count it. I mean, look around you. How many computers are within 6 feet of you right now? How many computers are sitting on your body at the moment? Do you have a smartphone on your pocket? Do you have an Apple Watch? Do you have a Bluetooth headset in your pocket? Do you have car keys? Do you have car keys with a little computer in them? Look on the walls. How many computers are on the walls right now? Do you have a thermostat on the wall? Go into your kitchen, right? Does the microwave oven have a computer? Yes. Does the refrigerator have a computer? Yes. Do the ovens, the washing machine, the dryer? Go into the garage. Look at the car. You got a car? You have a car? How many lines of code are in a modern car? Would you be surprised to find out that a modern car has 100 million lines of code in it? And what is that code? Most of it's in the GPS system and in the entertainment system, but some of that code is sitting between your foot and the brakes. When you put your foot on the brake, there are if statements in there. And wouldn't you like to know what those if statements say? Wouldn't you like to know how those if statements were tested? How many people have been killed because those if statements did not work right? Something went wrong with the computer or the software. The software lost its mind and the car accelerated out of control and rammed into a tree. How many people have been killed that way? And the answer is many dozens of people have been killed by software malfunctioning in their cars. You and I are killing people. We didn't get into this business to kill people, right? We got into this business because we wrote an infinite loop that printed our name on the screen once. And we thought, oh, yeah, man, that's what I want to do for the rest of my life. We didn't get into this business to deprive people of their lives or their fortunes. How many programmers are there today? I estimate somewhere on the order of 100 million. I don't know if that number's right. It's got to be somewhere in that order of magnitude, though. It's a lot of programmers. And let's just look at the trend. If there are 100 million programmers in the world today, which I don't think is an outlandish guess, well, 2 to the 27th is roughly 100 million. That means there were 27 doublings since 1945, since there was one programmer. Take the number 1 and double it 27 times, and you get the number 100 million. Now, how many years ago was that? 1945? Well, that was 76 years ago. So let's see, 76 divided by 27, that's about what, 2 point something? Does the number of programmers in the world double every 2.5 years? Actually, I think it's a little longer than that, because in the first couple of decades, I think the number was much higher, right? The first day there was 1 programmer, a day later there was 10, a month later there were 50. So the doubling rate was higher in the first decade. It's slowed down now to about maybe once every 5 years. Do the number of programmers in the world double every 5 years? Think of your past history. Think of the last N years. Does that look right? Does that feel right? It feels right to me, right? The number of programmers in the world doubles every 5 years. And that has a really interesting implication. Half the programmers in the world have less than 5 years experience. And this will always be true as long as we are doubling at that rate. Half the programmers in the world will have less than 5 years experience, which leaves our industry in a state of perpetual inexperience. And we are headed for a disaster. Maybe we've already experienced echoes of that disaster. We saw what happened with the 737 MAX. We saw what happened with Knight Capital when they lost $450 million in 45 minutes. We saw what happened with many other software catastrophes. But more important than that, civilization has come to depend upon us. This was not true 30 years ago. 30 years ago, civilization could have existed without us. It would have been hard because there were certain things done by computers. But 30 years ago, you could have gotten by. There weren't any computers in your washing machines. There weren't any computers in your cars. You didn't have to, use a computer at the store. They had manual cash registers, or some of them anyway did, right? So there were ways to live without computers. Today, there are no ways to live without computers. Software sits in the middle of everything. There is nothing you can do in the modern Western world without software sitting right smack in the middle of it. You can't cook a hot dog in your microwave. You can't wash your clothes. You can't drive to the store. You can't make a phone call. You can't watch TV. You can't buy anything. You can't sell anything. Nothing happens in our society without software being right smack in the middle of it all. Our civilization depends upon us in ways that it does not yet understand, and frankly, in ways that we don't understand really. But here's the bottom line, guys. We, programmers, rule the world. Other people think they rule the world, but then they hand those rules to us, and we transcode them into the programs that run on the machines that govern everything. You and I rule the world. We should talk to the leaders about how much tax we pay, but never mind all that. At some point, not too long from now, there will be a disaster of some kind. Some poor software idiot will do some dumb thing, and 10,000 people will die at a single shot. And when that occurs, and you know it will occur at some point. When that occurs, the politicians of the world will rise up in righteous indignation, point their finger squarely at you and me. Don't make the mistake of thinking that finger will go at your boss. It won't, because your boss will simply say, it was the programmers who did it. And they will ask us the question, how could you have let this happen? And we'd better have an answer for them. Because if our answer is, my boss told me it had to be done last Tuesday. If that's the answer that we give the politicians when they ask us that question, they will hang their heads in disgust and dismay. They will walk away and they will begin to legislate. They will pass laws that constrain you and I. They will tell us what processes we have to follow and what languages we have to use and what frameworks we have to use and what signatures we have to get and what books we have to read and what courses we have to take. And we will all wind up being civil servants working for the post office. This is a future I would like to avoid. How do we avoid that future? We cannot avoid the catastrophe. The catastrophe will occur. What we need to do is get ahead of it. What we need to do is be prepared so that when the politicians of the world point their finger at us and ask us how we could have let this happen, we have to be able to say, this was an accident. It was not due to our negligence. Because look, here are our disciplines. Here are our standards. Here is our ethics. This is how we enforce it. This was not due to our negligence. And today, we could not say that. The future of programming is the establishment somewhere soon of disciplines, standards, and ethics. We need to do what the doctors did. We need to get ahead of the game. We need to have this in place when government decides to regulate us so that we can provide the regulations to them. That's what the doctors did, right? Eventually, government went to the doctors and said, hey, we got to regulate you guys. And the doctor said, well, hey, here's all our rules. You can make them laws if you want to. We already enforced them. That's what we need to do. We need to get there ahead of time. And therefore, to prepare us for that, I present the following. An oath. This is just an oath. I kind of cooked it up. I said, okay, what promises am I going to make to myself, to my fellow programmers, and to the world at large about what I will do as a programmer? So I've got 10 of these. I'll go through them very rapidly and let's see what we come up with. Number one, I will not produce harmful code. This obviously comes out of the Hippocratic Oath, first do no harm. I will not produce harmful code. Now, obviously, this is ambiguous. There's a whole bunch of conscience issues here. What the heck do I mean by harmful code? That's really up to every individual to resolve or every organization to resolve. However, I will say that it's not just the behavior of the code that can be harmful. Code with poor structure is harmful. Does the code you write harm your fellow programmers by making it difficult for them to make progress? Do you write messy, tangled, horrible systems? Do you reach into the systems and add a new feature in the worst possible way just because it's maybe a little faster? Are you damaging the entire project? Are you damaging the entire industry by producing bad code? That's harmful. So that's another way to look at harm. Another of these oaths Number two, the code I produce will always be my best work. Now that's kind of a minimum expectation, right? I mean, it's going to be your best work. How many of you have shipped code that you knew was not your best work? I'll raise my hand there. I mean, but that should not be our expectation. Our expectation should be that when we release code, it's our best work. We will not knowingly allow code that is defective, either in behavior or structure, to accumulate. And the word accumulate is critical there. We are not perfect. We are going to ship some bugs. We are going to ship some bad structure, but we will not allow it to accumulate. When we see it, when we recognize it, we will improve it. Number three, I will, as a software developer, as a software craftsman, I will produce with each release a quick, sure, and repeatable proof that every element of the code works as it should. This seems to me to be a minimum requirement. Code is impossible for most people to read. Our customers do not understand it. Therefore, they need a proof that it works as it should. And we should be able to supply that proof. I recommend unit tests and acceptance tests as a way to demonstrate that proof, as a way to provide that proof. If you have a better way, that's fine too. I'm just saying that it's a minimum requirement from our customers, from our managers, that we be able to prove on a moment's notice that the software does what they expect it to do. 4, I will make frequent small releases so that I do not impede the progress of others. This is the commitment to work in small cycles. And obviously the reason behind that is that when you work in long cycles, you impede everybody else. Nobody else can get into what you're doing because you're holding the code out and you're not releasing it. And then when you do release it, there's a horrible merge to do and terrible bugs, and it's awful. So we're not going to do that. We're going to work in small cycles integrated with the rest of the team so that the team can behave in a fluid way. 5, I will fearlessly and relentlessly improve the work at every opportunity and never allow it to degrade. We're going to constantly look at what we have produced and constantly improve it. Human beings improve things with time. Entropy makes things go worse with time. Human beings fight that trend and improve things with time. This is just an oath to be human. Improve it with time. Number 6, I will do all that I can to keep the productivity of myself and others as high as possible. I will do nothing that decreases that productivity. You can interpret that any way you want. I'm not going to create messy code because that would be unproductive. I'm not going to throw tantrums in the office because that would not be productive. I'm not going to fight against the architects. I'm not going to fight against the design. I'm not going to undermine the project leaders. I'm not going to do anything that hampers productivity. I'm going to work as hard as I can to keep my productivity and everybody else's productivity as high as possible. One of the ways I personally do this is to write lots and lots of unit tests. That keeps my productivity very high. Number 7, I will continually ensure that others can cover for me and that I can cover for them. A team of software developers must be able to depend upon each other in a way where if one player goes down, if one member of the team goes down, the others can cover for them. You've seen this happen before, I'm sure. Bob is the database guy. Bob gets sick. Nobody else can do anything in the database because that's Bob's. Well, that's not acceptable. The rest of the team ought to be able to cover for Bob when Bob goes down. That means you're going to have to understand the database stuff. You may not be a database programmer. You may be a front-end programmer. You still need to understand the database stuff. You may not be a middleware programmer. You still have to understand what Mike has been doing in the middleware so that you can cover for each other. And look at the way this oath is phrased. I will continuously ensure that others can cover for me. It is your responsibility to go out to others and make sure those others can cover for you if you go down. 8, I will produce estimates that are honest both in magnitude and precision. What is the most honest estimate you can give? 3 little words: I don't know. That's the most honest estimate you can give, because that's the truth. You don't know. But that is not a useful estimate. So to make it useful, you have to give it a kind of precision. Right? You have to say, well, look, it's going to be sometime between this and then. I like to give estimates in 3 numbers: best case, nominal case, worst case. Look up PERT if you want to understand how that works. But I don't like to give dates. Dates don't work for me because I don't know if I can meet that date. I probably do know the probability distribution of when I might be able to get done. So that is both magnitude and precision. And the bottom line there, I will not make promises without certainty. Someone says, can you promise to get this done by next Thursday? No, I cannot promise that. I do not know if I can. I cannot be certain. I can tell you what the odds are, but I cannot promise that it will be done by next Thursday. I will not make those promises. Managers have to manage uncertainty. That's their job. They have to manage uncertainty. My job as a programmer is to tell them what the shape of that uncertainty is so that they can manage it. 9, this is just common decency. I will respect my fellow programmers for their ethics, standards, and disciplines and skill. No other attribute or characteristic will be a factor in my regard for my fellow programmers. Take that any way you want to, right? But that's just basic common human decency. And then finally, last one, I will never stop learning and improving my craft, not just your code, but your craft. You'll never stop learning because there's a lot of stuff to learn out there. And you will never stop improving your craft. That is the future of programming, I hope. That's where I would like to see it go. I don't know if these 10 rules are the best of the 10 rules. They're just kind of 10 rules that I cooked up a few years ago, and I've kind of tweaked them from time to time and thought, well, okay, it's a proposal. Take it as a proposal. Maybe you can tweak it better. Maybe you can make them better. But that's where I am today. And that's what I think the future of programming is. And that is the end of my talk. Thank you all for your attention and for listening. I hope you learned something. I hope you enjoyed it. And we have 10 minutes left for any questions that you might have for me.
Right. Actually, there are several questions in Slack. Well, thank you very much for the talk, because I mean, it was really amazing. There's a lot of, commands. People like your talk. And the first question that popped up, where do you take the energy?
Where do I what?
Where do you take this? Where is your source of energy to make this energetic talks?
Oh, what is my source of energy? I love my industry. I love software. I love talking about it. I love speaking. The energy just comes from my sheer enjoyment of what I am doing at the moment. After I'm done with this, I will go collapse and take a nap.
Yeah. So another question, given the number of programmers double every 5 years, will we come to a point where some programmer will become obsolete, and because everybody will be a programmer?
So that's a really interesting question. Will everybody become a programmer? My experience is that there are people who cannot do this. And that was a big surprise to me. I found that out by hiring a few of the wrong people. And there was no way I could get them to conceive. I thought they were bright people. They could do a lot of interesting mathematics. I used to hire people based on their ability to solve mathematical problems. And then I would run into these people who were fine doing that, and they could not write code. Could not. And so I don't know if everyone will become a programmer. I think, however, it is a safer bet to say that information work, the kind of work that you and I do, coding and other informational work, will be the largest single job function in the world.
Yes, so we talk about the programmers, but what do you think about technology? Will it ever stop evolving, or will be some plateau?
Will the technology ever stop? The way technology works is it goes in phases. There's these rapid exponential bursts and then these long plateaus, and then a rapid exponential burst and a long plateau. We are currently on a plateau. I expect that plateau to last for many decades. Mm-hmm. Some very unusual thing is going to have to happen for us to bump that up into another exponential run. And I don't think it's quantum computing. You know, so as much as people talk about quantum computing, I don't think that's going to be it. And I don't think it's going to be machine learning or artificial intelligence. I think that's just a symptom of being on the plateau. The next exponential curve, I don't know what that's going to be, but it'll probably come.
But can you predict what will happen, or what will happen next in software development? Like any type of new programming, type of languages, high level, high orders?
No, on the plateau, I don't expect much to happen. I expect a lot of churn. I expect a lot of this kind of stuff, a lot of heat without a lot of light. The new languages coming out are not really new. The new processes coming out are not really new. The new frameworks coming out are not really new. They're all just a rehash of older stuff. And I expect that to continue for several decades. This churn without any real progress. There will be at some point, I hope, some kind of technological awareness or revelation, and then we'll enter the exponential curve again.
Mm-hmm. But do you think that maybe, you know, now most of us, we are programming at our local computers. Do you think that this will probably jump into the cloud and we're going to use supercomputers or like farms of huge farms of computers to do the same thing?
Yeah, there's a lot of that going on already, and that is fairly mundane. You know, okay, we can recruit 1,000 computers and do a nice MapReduce thing, and okay, we're splitting it across, but we do not have a network that is capable of tying these computers together at the bandwidth that would be required for any kind of really revolutionary thing. You know, even when you're talking about gigabits, it's still too slow to tie thousands of computers together into, oh, for example, consciousness.
Yeah. Right. Yeah, there's another question from the audience. I know that your favorite language is Clojure, right?
At the moment, yes.
Yes, and I mean, Clojure basically is Lisp, which was invented in the 70s. Do you think that maybe some other languages like Prolog or, I don't know, Fortran will have a comeback and have another life in the future?
Resurgence of Fortran. I do not expect a resurgence of Fortran. And I do not expect a resurgence of logic languages like Prolog. They were all the rage in the 70s and the 80s. There was a time when everybody said the Japanese are going to take over everything because they're writing in Prolog. Yeah, well, that didn't happen. And, you know, Prolog is a very interesting language, but that's about what it is, an interesting language. It's not a very productive language. Do I expect some new language to suddenly become the key that drives us all into the next, you know, century? No, I don't. I don't expect a new language to be any better than what we currently have. Right. One of the reasons I like Lisp, one of the reasons I like Clojure, is because it sits on top of the JVM, so it's got a tremendous amount of resources behind it. But it is as simple as a language can be, and that makes it very expressive. So that you have the advantage of this simplicity and expressivity sitting on top of a vast wealth of resources.
Yeah. And maybe the last question: what is the single most important career advice you would give to a new developer or senior developer?
The most important advice, right? And now, Senator Mancuso said something that I thought was very profound. He said, you know, you are far more than a software developer. I hope this talk has emphasized something like that. You are not just a software developer, you are an ethical being. You are a professional being. There is more to this than just writing a lot of code. The advice I would give you as a developer is to read a lot, and read stuff outside of your field. Read some philosophy, read some ethics, read some old and new stuff. Read old books in the field. Go back to the early days of software and read some of the early works of guys like Dijkstra and Tony Hoare and Ole Johan Dahl and people like that. And you will find hints of this ethics in there. You will find hints of standards and disciplines buried in that work. They hadn't conceived entirely of it, but the knowledge was there. They were trying to ferret that stuff out. Learn how to write. And I mean write in your native language.
Yeah.
Learn how to organize your thoughts and put those thoughts down on, I would have said paper, but now it's on your screen. Put those thoughts down on your screen in an organized way so that other people can consume them. And by the same token, learn how to speak, learn how to debate, learn how to talk to people respectfully, but convincingly, right? These are talents that most programmers find elusive because they don't like working with people, really. So we didn't get into this business because we like people. We like machines. And it's a talent that is necessary if you're going to be part of a team and part of a profession.
Yeah. Thank you. Thank you very much.